Hello, my name is Mac Liu. I'm the International Sales Manager for Listen. So I'll talk about two topics. First one is what we call open loop testing. And the second topic will be about Bluetooth. So I'll demonstrate what SoundCheck can do in both applications. And of course, if you have questions, please don't hesitate to ask. So, the difference. Traditionally, we have what we call a closed loop test system. Very simple in terms of concept. Steve have talked about loudspeakers and headphones. The common link there is it's a single loop. So if you're testing a transducer, headphones, speakers, all those things are connected to a single amplifier and a single sound card. So what's important there is the sampling rate is the same in the loop. And also there's only one crystal clock for the timing. So the analysis is still done by the computer, but there is no different sampling rate. There's only one, and there's only one clock. So the frequency is the same, and the sampling rate is the same in the whole loop. What's different now is there's a lot of new requirements where you have to test a complete device, a device that is not just a transducer, but maybe a smartphone that is a finished product. The phone has the microphone and the speaker already inside. So there's no wires connected to it that you can easily connect to for testing. Or you have a device like this, a Bluetooth speaker. Again, same thing. It's a finished product with transducers inside, but you cannot connect a wire directly to the transducer. So because there's no wiring, the sampling rate and also the clocks are different. You have more than one. Here, the device itself could be at a different sampling rate than what the source speaker is putting out and what's being recorded. So that's what we call an open loop test. It's open because there's no connection to complete the whole test system. So we already talked about some of the differences between closed loop and open loop. Mainly look at the chain of the test loop. You have a sound card, and it goes to the amplifier, which goes to the speaker, back to the microphone. So you sent out a stimulus here, and the microphone responds or captures the response, acquires the response, back to the audio interface, to the computer for analysis. So input and output are in the same domain. It's analog. And they're synchronous, so they have the same sample rate. Like I said before, same sample rate, same clock. However, if you have open loop, the input and output could be in different domains. You could have an output in analog, but your input could be digital, like a Bluetooth speaker. And they could be different crystal clocks in them. So the sampling rates, the input output are asynchronous, and also there's also variable delay between input and output. So those are problems that we have to deal with that don't exist here in closed loop, but are very common in open loop. So when you have input and output in different domains, analog versus digital. You have to be careful about your calibration, and you have to set up your signal path. And so you have to basically create equivalent calibration based on the type of signal you're getting. For example, if it's digital, in soundcheck, based on the AES 17 standard, it's 1.414 full scale per full scale for output, 0.707 full scale per full scale for input. So this is just an example of the calibration that needs to be set up inside soundcheck. And if you have different sample rates and phase, you have to do two things. First, you resample based on the, because there's a big difference in the sampling rate. Let's say 44.1 kilohertz is one response, and your other response is at 48 kilohertz. There's a big difference in the sampling rate. So therefore, you have to go through a what we call a resample step. I will show you how that works in soundcheck. And if it's a crystal clock difference, it might be a very small difference. 47.999, let's say for one timing. The other one is 48.01. It's a very small difference, but over time that becomes a bigger problem. So this is another step that we have to take as well. It's called frequency shift. And that can be done in soundcheck. So two steps, when the output and input are asynchronous, means they don't have the same sampling rate and they don't have the same crystal clock. So resample and frequency shift, two steps. And they're very easily set up in soundcheck. It's not a difficult thing to do. And if there's delay between input and output, there's also another step that you can take in soundcheck called auto delay. And it will automatically line up the stimulus to the response in soundcheck by using auto delay. There's a little bit of a problem. If your delay is greater than 2.5 seconds, then this might not work as well, but I will show you a way to rectify that problem in soundcheck. It's actually quite easy. You just have to make some adjustments to the waveform. So basically make sure the waveforms are within about 2 seconds of each other's timing. So this is just a quick graphical representation of what goes on within soundcheck. You have your stimulus, which is sent out by soundcheck to where you get a response. So what we want to get to is make sure these two, because this is where the magic happens. Soundcheck takes these two waveforms, analyze them, and you get frequency response, THD, perceptual rub and buzz, things like that. And if these two are not in the same sample rate, soundcheck will tell you that. They'll say, it will tell you you're not working the same sampling rate with the frequency, the stimulus and response. So you'll know you're in trouble when you don't have matching sampling rates. But if it's just a slight difference in the clock crystal, where it's just say 47.999 kilohertz versus 48.01 kilohertz, it won't tell you that. But you should know that there's a difference in the clock crystals and make sure you do frequency shift when you're comparing the two waveforms. So when in doubt, always just resample and frequency shift. It won't hurt anything. It will be, then you'll definitely make sure you have the right analysis completed. So we can get to a demo. Now this is just what we call a playback only. What I want to do is I want to test. Here's my little iPhone here. I have 2 speakers in here. I want to test the speaker of this completed iPhone. And many reasons for doing that. Even though the transducer might have tested okay before it went into the phone, but maybe after production, there are things happening inside that could have altered the performance of the transducer. For example, whatever loose particles might get in there. There's rub and buzz that could happen after it's already been installed inside the phone. So you can use this process to test the completed phone and catch any rub and buzz, loose particle, things that are defects. So to do that, first step is we set up a trigger tone. And because I don't know when I want to test, I'm going to put a stimulus on this phone so I can play back through the speaker. But I don't know when I'll be able to press the button to play to when actually gets recorded. So what I can do is I can set up a trigger tone to the stimulus. So SoundCheck knows I won't do anything until I have a trigger. Once I have the trigger, I can start recording my response. And once it's set up, the stimulus is set up with the trigger tone, you can save it as a WAV file. Now this WAV file, I can take it and put it into my phone, into any device that allows me to store a WAV file to play back. And once it's set up, you have a triggered record-only acquisition step in your sequence to acquire the sequence, to acquire the response from the speaker. And after it's acquired the response, you need to resample and frequency shift. And then after that, you do your analysis just like you would all the other tests or analysis you want to do. So let's look at how we do this. It's probably a little hard to see here, but this is a very simple sequence that is written to do the testing we want to do. So let me grab this is just our measurement microphone to test the speakers. And the first step, here's the stimulus that we're using to do the testing. You can see here is this just a regular 1K test tone. And then we add a little bit of kind of silence to give it time to get ready to do the measurement. You can see it's right here in the middle. So here's your test tone, a 1 kilohertz signal, and then there's a little bit of a gap, and then we just do a quick log sweep, starting at 10, stopping at 20 kilohertz. So this is a signal, test signal, that we can store as a WAV file. So you just come down here, save as, and you can call it whatever signal you want, xlog, tsr, and it will save as a stimulus file, or sorry, that's if you want to save it as a unique name. If you want to load it, where's the... output path. Steve, how do you export the file, WAV file? Memory list, that's right, sorry. Forgot about that. So that is the stimulus, where you have the test tone and the silence and then the sweep. And if we go to the memory list, here we have our stimulus waveform right here. If we right click, we can save data as .wav file. And now you can put it anywhere you want as a WAV file and move it to a place where you want to store it to playback. I happen to have it downloaded, but it's on my phone, and I'll play it back as soon as I finish downloading here. So I emailed the WAV file to myself yesterday, so it worked yesterday, but now it's working again. So all of this is just an attachment, .wav file attachment. So on my iPhone, there's a test tone. And that's the log sweep, just a quick waveform. Now, we can do this by, of course, this is just for a demonstration. In a production line or in a factory, you probably have an automated process, maybe a test box. This environment is not the quietest, but of course, a test box with an automated process can be done where you transfer the file onto the device you're testing and automate that in a quick process. So if I start my sequence, it's just waiting. Talk about triggered record. Right now it's not doing anything. But if I play my stimulus, it triggered the response to record. Now it's telling me that it's not the same sampling rate. Wait, let me try again here. And let's try it again. Second time's the charm, hopefully. Okay, now it's waiting for my trigger. Voila. You have your frequency response, THC normalize, and perceptual rub and buzz. The data looks, it doesn't look right, but that's how you could do just a playback only test. Okay, so that's a playback only. So next type is record only. So again, we have a smartphone or any device that we want to test, but instead of testing the speakers, we want to test the microphones. So it's a record only now application. It's a little more complicated, but still very easily managed. You still need to have a stimulus step, just like we have before. And you want to make sure the, ideally you want to make sure the output channel has the same nominal sample rate as the playback device. That's not always possible. For example, a Bluetooth speaker. But if you can't, either way you can make it work. You have to use a signal generator in your sequence to generate a signal. And you can do that through a speaker, a source speaker, to generate that signal. And then you have to, once you've generated a signal from the source speaker, you make sure there's a way to record that in your device. And for our example, my iPhone, I just went online to a app store and I downloaded an app that allows me to record sound in a waveform. So that way I can record it on my phone on whatever comes out of my source speaker. And then you have to use a recall step to pull the recorded waveform response into soundcheck. And then you do resample and frequency shift, just like we talked about before. After that, everything else is the same. So it's a little more involved in that you have to find out a way to record on your device, and then once it's recorded, take that file and recall it back into soundcheck for analysis. And resample and frequency shift. Let's look at this in soundcheck. All right, let's look at the sequence a little bit. We have a stimulus that we're going to generate, and it's going to tell here's a message step, it's going to tell the operator to start recording. I have a little iPhone app here. It's just a microphone. If I press record, testing 1 2, testing 1 2. I can play it back. Testing 1 2, testing 1 2. So I managed to record something in a waveform, .wave file, and I can, after I do that, I can move the WAV file around by email or put it on a network. So that again could be automated. The system, how that's set up, is really up to you to figure that out. So once I record the message, it's gonna say, all right, why don't you stop and copy the WAV file and import it somewhere, put it on the computer or somewhere you can get to. And here's my recall step. It recalls the waveform into a soundcheck and does the analysis. First, it's going to look at the waveform and say, okay, I want to be able to figure out. We talked about delay earlier. That if the delay is more than 2.5 seconds, there's maybe trouble to line them up. So in this sequence, where we just made it pretty manual, it's going to show us the waveform, and then we can look at where this response actually starts, and then we can chop off the part that we don't need. So it's a nice little example of how that could help lining up the timing, so it's not more than 2.5 seconds. Once we've done that, it's going to go through the resample frequency shift steps to make sure we have everything is aligned perfectly, does the analysis, and then shows you the response of the microphone. So let's do it. There's a message says, begin recording on device. Press enter to continue. So I'm going to go to my little handy iPhone app. I'm just going to press record. Pretty close to this. Maybe I'll just, press record. I'm going to enter. It opened up the signal generator to play the stimulus. And now I'm going to press stop. Now I have the response saved on my phone in a .wave file, and it says transfer to the computer. Now this is kind of kludgy, it's manual, but there's ways to automate this, and it can be done with SoundCheck. So luckily I'm going to cheat a little bit. I already have my response saved on my computer, and it says, it's right here, open loop microphone response. Press OK. SoundCheck just looked at it and said, hey, this is the response I got. And you notice up about 2.5 seconds is just nothing. That's more than what we want. So it's saying, hey, why don't you look at your response and tell me when I should start analyzing within about a second. And it's pretty obvious 2.5 is good enough. So I'll just say 2.5. So SoundCheck basically windowed the part that it wants, cut off the rest, and did analysis on this waveform. And there is my response. So just kind of beat it to death. Resampling and frequency shift. They're required anytime the output and input are not in the same device, meaning there's no closed loop, if it's open loop. Definitely resample when the wave response and stimulus don't have the same sample rate. One is 44.1, the other one is 48K. SoundCheck will tell you that there's a problem, like we saw. It says, hey, these waveforms aren't matching. So you should resample. So this is easy to fix. We know that something is wrong when the sample rates are wrong or not matching. This one is a little harder, even though they're the same sampling rate, but they have different clock crystals. So your frequency, the sampling rate will be different by a little bit. Not here, this is a lot. This is just a little bit. So SoundCheck will not give you an error when it's just, it's not the same device but the same sampling rate. Eventually the results will be incorrect in that it's really proportional to the sample rate mismatch. So if it's missing by a little bit, the error will be a little one, but it's missing by a lot, the error will be big. But if it's missing by a whole lot, it'll tell you there's something wrong. So when in doubt, resample and then frequency shift. Like I said before, it doesn't hurt to do these two steps. SoundCheck will like you better if you do this. and not give you an error. So some other things to watch out for, to be careful of, besides resampling and frequency shift. Use auto delay to line up the timing of the responses. You can manually trim, like we did, cut off the part that we don't want. Make sure they're within the certain 2.5 seconds of each other. If the frequency response looks funny, that's a sign that you do need to do a frequency shift, if in case you didn't do that already. And you have to make sure there's enough time for the operator to do what they need to do as well. So there's timing involved in if there's a line set up and the operator is having to do certain things, make sure you account for that timing on that delay from the operator working. And you could combine different stimuli and responses for multiple different measurements. You just have to take the acquisitions apart by using windowing to get the parts you want. And this is for the playback only, and you could also do that for record only. Okay, in summary, anything you can make in terms of measurements in a closed loop, you can also make an open loop. And it's any measurement, any stimulus type. There's no restrictions on the fact that you have a traditional measurement where you have a closed loop versus open loop. You do have to take some steps to account for the differences in sampling rate by resampling and frequency shift. But essentially, anything you can do in closed loop, you can do in open loop. Devices that we can test, smartphones, MP3 players, Bluetooth speakers, etc., etc.